Right now, while you're watching this video, something is happening that almost nobody on Earth is paying attention to. Hundreds of enormous steel gates are resting beneath seawater at the edge of one of the world's most famous cities. Most of the time, they are completely invisible. Tourists walk through ancient streets only a few kilometers away. Boats pass overhead. The tide rises, the tide falls, and beneath it all, an engineering system waits. It is not a bridge, it is not a dam. It was designed before smartphones became common, before social media connected billions of people, before many of today's visitors to Venice were even born. Together, these submerged structures stretch across the three inlets that connect the Venetian lagoon to the Adriatic Sea. Imagine dozens of hollow steel chambers, each roughly the length of a passenger jet, lying flat on the seabed, waiting for the sea to reach a precise level. When that moment arrives, they rise together, slowly, silently, and, for a few critical hours, they separate an entire city from the sea. For decades, engineers believed they represented one of humanity's greatest defenses against coastal flooding. But reality has turned out to be more complicated. The researchers and engineers involved are not describing the challenge with words like interesting. Instead, official reports increasingly discuss maintenance, corrosion, rising costs, changing sea levels, and uncertain long-term performance. This is the story of Venice's most flood barrier system. And here is the part the headlines are not telling you. It is not just about protecting Venice. It is about what Venice is teaching every coastal city that hopes to fight a rising ocean. It is about what is happening to the barrier system right now, years after it first became operational. And it is about what scientists and engineers expect over the coming decades as sea levels continue to rise. Stay with me, because by the time this is over, you will never think about flood barriers or the ocean that surrounds them the same way again. Before we begin, if you enjoy calm, evidence-based documentaries that explain real scientific discoveries without the exaggeration, consider subscribing. Every episode here is built from published research, engineering reports, and historical records, not viral headlines. Now, let's go back to where this story actually begins. In November 1966, Venice experienced one of the worst floods in its recorded history. For nearly 22 hours, unusually high tides, combined with strong winds, pushed seawater deep into the city. Water levels reached approximately 1.94 meters above the local reference level. To picture that, imagine seawater climbing higher than the average adult standing on the pavement. Thousands of homes flooded, historic churches filled with salt water, libraries lost priceless books, businesses shut down. Residents watched centuries of history disappear beneath muddy water. For Venice, flooding was nothing new. The city had always lived with acqua alta, literally high water. But this flood was different. Its scale forced Italy to confront a question that had been growing more urgent for decades. Could Venice actually survive the future? The city itself was already sinking slightly because of natural geological processes. Earlier in the 20th century, groundwater extraction had made that sinking even faster before pumping was eventually reduced. At the same time, global sea level was slowly rising. Neither process alone seemed catastrophic. Together, they meant something very different. Every future storm would begin from a slightly higher starting point. Think about climbing a staircase. If someone secretly raises the floor by just a few centimeters every year, eventually, the same staircase becomes much easier to reach. That is essentially what rising sea level does to coastal flooding. The storm itself may not become dramatically stronger. The water simply starts higher, and that small difference changes everything. Following the disaster of 1966, engineers, scientists, architects, and politicians spent years debating possible solutions. Some suggested raising the city itself. Others proposed enormous seawalls. Some argued Venice should simply learn to live with increasingly frequent flooding. None of those ideas solved every problem. Protecting the city without destroying the natural lagoon proved extraordinarily difficult. The Venetian lagoon is not merely empty water surrounding Venice. It is a living ecosystem. Tides move nutrients. Fish migrate. Sediments shift. Wetlands depend upon regular exchanges between sea and lagoon. Blocking that exchange permanently would protect buildings, while slowly damaging the environment that helped create Venice in the first place. The challenge seemed almost impossible. Protect the city, but do not isolate the lagoon. Stop dangerous floods, but allow ordinary tides to continue. Build something massive, yet leave it invisible most of the time. Those competing demands eventually led engineers toward one remarkable idea. Instead of building permanent walls, why not build walls that only existed when they were needed? The concept gradually evolved into what became known as MOS. The name comes from the Italian phrase modulo sperimentale elettromeccanico. It also deliberately echoes the biblical story of Moses parting the sea. The basic principle appeared surprisingly simple. Most of the time, the barriers would remain filled with water and lie hidden on the seabed. Ships could move normally, tides could flow normally, marine life could continue largely unaffected. Only when forecasts predicted exceptionally high tides would compressed air push water out of the hollow steel gates. As they filled with air instead of water, they would become buoyant. Slowly, the gates would rotate upward, one by one, until they formed temporary walls separating the Adriatic Sea from the lagoon. Once the danger passed, water would return inside. The gates would sink. The sea would reconnect with the lagoon. The city would continue as though nothing had happened. On paper, it looked like one of the most elegant flood control concepts ever proposed. A defensive wall that spent almost its entire life hidden beneath the sea. A city protected, without surrounding it with permanent concrete barriers. An engineering solution, unlike almost anything ever attempted. But turning that elegant idea into reality would take decades. It would cost billions of euros. It would survive political controversy, construction delays, corruption investigations, redesigns, and constant engineering challenges. And even after becoming operational in 2020, the hardest questions were only beginning. Because building a flood barrier is one challenge, keeping it reliable for decades inside warm, salty seawater is an entirely different one. To understand why the MOS system became one of the most ambitious engineering projects ever attempted, you first have to understand the problem it was built to solve. The Adriatic Sea does not simply crash into Venice like waves striking a beach. Most flooding arrives much more quietly. It begins with the tide. Normally, tides enter the Venetian lagoon through three natural openings: the Lido Inlet, the Malamocco Inlet, and the Chioggia Inlet. Think of them as three large doors connecting the lagoon to the sea. Every day, water moves through those doors. The lagoon rises. The lagoon falls. That daily exchange is essential. Without it, the lagoon would gradually become unhealthy. Sediment would accumulate differently. Water quality would change. Marine ecosystems would suffer. So engineers faced a difficult balancing act. They could not permanently close the inlets. They only wanted to close them when exceptional tides threatened Venice. That single requirement shaped everything that followed. The barriers begin their normal life underwater. Each gate is a hollow steel structure attached to a massive concrete foundation on the seabed. When the gates are resting, they are filled mostly with seawater. That makes them heavy enough to remain flat on the bottom. Invisible to ships, invisible to visitors, invisible to almost everyone passing overhead. Only when forecasts predict exceptionally high water does the process begin. Powerful compressors pump compressed air into each gate. That air pushes seawater back out. As water leaves, the gates become lighter. Eventually, they become buoyant. Buoyancy is simply the upward force produced when something becomes lighter than the water surrounding it. You see the same principle every time an empty plastic bottle floats, or when a life jacket keeps someone above the surface. The MOS gates use exactly the same physics, just on an enormous scale. Instead of floating away, each gate rotates upward around giant hinges fixed to the seabed. Slowly, deliberately, one after another. Eventually they rise above the water surface, creating a temporary barrier between the Adriatic Sea and the lagoon. When the dangerous tide has passed, engineers reverse the process. Air leaves, water flows back inside. The gates become heavy again. Gravity lowers them back to the seabed. The lagoon reconnects with the sea. Everything returns to normal. At least, that is the theory. On paper, MOS solved problems that older flood barriers never could. Permanent seawalls create permanent consequences. Ships cannot pass easily. Tides change forever. Marine ecosystems adapt, or disappear. The MOS system avoided those problems by spending almost all of its life underwater. Imagine owning an umbrella that only appears above your head exactly when rain begins, then disappears again as soon as the clouds leave. That was the engineering philosophy. Protection only when necessary. No permanent wall, no permanent disruption. For decades, engineers around the world admired the elegance of the concept. The mathematics worked. Hydraulic models worked. Computer simulations suggested it would protect Venice from exceptionally high tides. But engineering calculations happen inside computers. Reality happens inside seawater. And seawater is one of the harshest environments any machine can face. Steel is incredibly strong. Saltwater is incredibly patient. Every engineer working near the ocean understands one simple truth. The sea never stops working. Every hour, every day, every year. Salt attacks protective coatings. Tiny marine organisms attach themselves to metal. Sediment settles. Currents shift. Moving parts wear. Think about leaving a bicycle outside through years of rain. Eventually, rust begins to appear. Now imagine leaving machinery underwater. Not for 1 year. Not for 10 years. But for decades. And instead of rain, the machinery sits inside warm, salty seawater, every minute of every day. That is the environment facing every hinge, every seal, every hydraulic connection, every steel surface inside the MOS system. Researchers understand corrosion extremely well, but predicting exactly how thousands of interacting components will age over decades remains much more difficult. Real structures often surprise engineers. Tiny differences accumulate. Materials behave differently than expected. Maintenance schedules evolve. That uncertainty exists in almost every major infrastructure project. MOS is no exception. Now consider another challenge. Most large machines can be repaired easily. A bridge can be inspected from above. A train can enter a maintenance depot. An aircraft returns to an airport after every flight. The MOS barriers do none of those things. Most of the time, they remain underwater. Access itself becomes an engineering project. Divers, specialized vessels, temporary closures, complex inspection procedures. Every major intervention costs time, money, planning, and weather conditions that cooperate. Now multiply that by dozens of massive gates spread across 3 separate inlets. The scale becomes difficult to appreciate. Imagine maintaining the moving parts of dozens of passenger jets. Except every aircraft spends its life underwater. That comparison is not perfect, but it captures the challenge. The gates are not simply large. They are large, hidden, marine, and expected to work precisely when the city needs them most. Because flood barriers have one job. They do not have to impress tourists. They do not have to operate every day. They simply have to work perfectly, on the few days when failure would matter most. And beginning in 2020, engineers finally had the opportunity to test the system under real conditions. What happened next surprised both supporters and critics. The barriers successfully protected Venice during several exceptionally high tides. But success did not end the debate. Instead, it opened an entirely new one. Because the question was no longer, can MOS work? It became, after decades of planning, years of construction, and billions of euros in investment, the MOS barrier finally faced the challenge it had been built for. In October 2020, exceptionally high tides threatened Venice once again. Forecasts predicted that water levels would reach heights capable of flooding much of the historic city. This time, engineers activated the barriers. Compressed air entered the gates. Water flowed out. One by one, the steel structures rotated upward. For the first time, under genuine storm conditions, the Adriatic Sea was temporarily separated from the Venetian lagoon. Inside the city, something remarkable happened. The expected flooding largely did not arrive. Areas that would normally have disappeared beneath seawater remained dry. People could continue walking through St. Mark's Square. Businesses stayed open. Historic buildings escaped another cycle of saltwater damage. For many engineers who had spent decades working on the project, it was an emotional moment. The system had done exactly what it had been designed to do. But engineering projects are not judged by a single successful day. They are judged by years, then decades, and eventually, by generations. That is where the story becomes more complicated. It is tempting to think of MOS as a permanent solution. In reality, it was never intended to eliminate flooding forever. It was designed to reduce the impact of exceptionally high tides. That distinction matters. The barriers are raised only when forecasts exceed a predefined threshold. Closing them too often creates different problems. Remember those 3 natural openings connecting the lagoon to the sea. Closing them interrupts the normal exchange of water. That exchange carries oxygen, nutrients, sediment, marine life. If the lagoon remained sealed for long periods, water quality could decline. Scientists continue studying exactly how repeated closures might influence the lagoon's ecosystem over many years. Some effects are understood, others remain difficult to predict. Natural systems rarely respond in perfectly simple ways. Researchers still cannot fully explain every long-term interaction between changing tides, sediment movement, and biological communities. The lagoon itself is constantly evolving, and any structure built inside it becomes part of that evolution. Now consider another number. Global average sea level continues to rise. Not everywhere at exactly the same rate, not by exactly the same amount, but the long-term trend is clear. That changes the operating conditions for every coastal defense system on Earth. Imagine placing books underneath a table. One book might not seem important, then another, then another. Eventually, the table sits noticeably higher than before. Sea level rise works in a similar way. Storms that once barely caused concern now begin from a higher baseline. That means the barriers may need to be activated more frequently than engineers originally expected. More activations mean more movement. More movement means more mechanical wear. More maintenance, more inspections, more operational costs. This does not mean the system is failing. It means the environment it was designed for is gradually changing. Infrastructure built for one climate may face different conditions several decades later. That challenge extends far beyond Venice. Cities from Miami to Rotterdam, from Shanghai to Jakarta, are asking similar questions. How do you build something today that must still work in a different climate tomorrow? No engineer has a perfect answer. This is where headlines often become misleading. You may see phrases like, "The barriers are already failing." Reality is more nuanced. The MOSE system has protected Venice during multiple high-water events since becoming operational. At the same time, public reports have documented maintenance needs, corrosion concerns, component replacement, operational challenges, and continuing costs. None of those observations are surprising for a complex marine engineering system. Every large infrastructure project requires maintenance. The real question is not whether maintenance exists. The real question is whether maintenance can keep pace with decades of environmental change. That question remains open. Researchers continue monitoring the barriers. Engineers continue improving inspection procedures. Government agencies continue evaluating long-term operating strategies. No single report has closed the debate. Perhaps the biggest surprise is that MOSE is no longer just an Italian engineering project. It has become a global experiment. Every coastal engineer is watching. Every city planning new flood defenses is paying attention. Not because Venice found a perfect answer, but because Venice is revealing the real-world challenges that computer models alone could never fully predict. The steel gates may stand between the sea and one historic city, but the lessons they produce belong to every coastline on Earth. And the next chapter of this story may prove even more important than the first, because protecting Venice is one challenge. Protecting Venice for the rest of this century is another entirely. When engineers designed MOSE, they were not trying to stop the sea forever. That would have been impossible. Instead, they were trying to buy time. Time for Venice. Time for its residents. Time for its historic buildings. Time for future generations to decide what comes next. That distinction is easy to miss. Engineering is often portrayed as solving problems permanently. In reality, many of the world's greatest engineering projects simply delay consequences long enough for society to adapt. A levee buys time. A reservoir buys time. A seawall buys time. MOSE buys time. The question is, how much? No one can answer that with certainty, not because the system is poorly understood, but because the future itself is uncertain. Scientists can project global sea level rise using different emissions scenarios. They can model storm surges. They can estimate changes in tides, but they cannot predict the exact sequence of storms that Venice will experience over the next 50 years. Weather does not follow a script. Neither does the ocean. That uncertainty is not a weakness in science. It is simply the reality of forecasting complex natural systems. Venice has survived for more than 16 centuries. That fact alone is remarkable. The city was built on wooden piles driven deep into soft lagoon sediments. At first glance, that sounds impossible. Wouldn't wood rot underwater? Normally, yes. But beneath oxygen-poor mud, the timber remains preserved because the microorganisms that usually break down wood cannot thrive in those conditions. It is another reminder that Venice has always depended on a delicate balance between nature and engineering. The lagoon protects the city. The city depends on the lagoon. Change one too much, and both begin to change. This relationship has existed for centuries. Mos is simply the newest chapter, not the first, and almost certainly not the last. Long before steel flood barriers existed, Venetians were already redirecting rivers, reinforcing islands, and managing waterways to preserve the lagoon. Each generation inherited a different version of the same challenge. How do you live in a place where land and sea never stop negotiating with one another? That negotiation continues today. Only now, it includes climate change, modern engineering, satellite observations, computer forecasting, and one of the largest movable flood barrier systems ever built. Even today, researchers continue studying questions that do not yet have complete answers. How will repeated barrier closures influence sediment transport over several decades? Will changing sea levels require the gates to operate more frequently than originally anticipated? How will maintenance strategies evolve as the infrastructure ages? Can corrosion rates be reduced through improved materials and protective coatings? These are not signs that the project has failed. They are the normal questions that accompany every major engineering system. Think about commercial aviation. Modern aircraft are extraordinarily reliable, but engineers never stop inspecting them, never stop improving them, never stop learning from every flight. Mos is no different. Every activation provides new data. Every inspection reveals new information. Every year improves scientists' understanding of how such a system performs in the real world. Researchers still cannot fully explain every long-term interaction between infrastructure, sediment movement, marine ecosystems, and a changing climate. And that honesty matters. Science advances by identifying uncertainty, not by pretending uncertainty does not exist. It would be easy to think this is only a story about one Italian city. It is not. Nearly half of the world's population lives within a relatively short distance of a coastline. Many of the world's largest cities face rising sea levels, stronger coastal flooding, or both. Each location is different coastlines, different tides, different geology, different weather. There is no universal solution. The flood barrier that works in one place may be completely unsuitable somewhere else. That is why engineers around the world continue studying Venice so closely. Not because Mos provides every answer, but because it reveals the questions future projects must ask before construction even begins. How often will it operate? How expensive will maintenance become? How will ecosystems respond? How will climate conditions change over the next century? Those questions are becoming increasingly relevant, far beyond the Adriatic Sea. So what does all of this actually add up to? A city built on water, protected by machines hidden beneath the sea, waiting patiently for tides that arrive only a handful of times each year. 3 inlets, 78 movable gates, 1 lagoon that has never stopped changing. Those numbers tell an engineering story, but they also tell a human one, because every generation believes it has finally solved the greatest challenge it inherited. Then nature quietly changes the conditions. Venice has never been a city that defeated the sea. It has always been a city that learned to live with it. Mos is the latest expression of that centuries-old relationship. Whether it continues protecting Venice throughout this century will depend not only on steel and concrete, but on careful maintenance, continued scientific research, and decisions that have not yet been made. The story, in other words, is still being written, and that may be the most important lesson of all. If you enjoyed this documentary, consider subscribing and turning on notifications. Here, we explore the world's most remarkable engineering achievements and natural phenomena through evidence, historical records, and published scientific research, rather than exaggerated headlines. Thank you for watching.